Hi everyone, Mr. Lee here. In this video, we're going to go over centripetal forces. Now, centripetal means center seeking, and the object or system is going to be rotating in a circle either partially or fully. And this is what I mean by that. Let's imagine a car. So if this is an aerial view of a road and we have a car right here, okay, and this is like a roundabout, and if you're going around the roundabout, just going around in a circle and around in a circle, 360 degrees, you are fully rotating. But let's say you're just driving in a car, right? And then you want to make a right-hand turn onto the road. So if you're driving and you're making a right-hand turn without stopping, okay, you see this right here. If I highlight this part, that's a part of a circle, because if I were to continue that around, like so, okay, that path around, we will get a rotating or a circle. So even if you're turning to the right, you're considered to be partially moving in a circle because you're creating like a arc of a circle. So any time that you are either 100% going a circle or partially going a circle, there's centripetal forces being applied. All right. Now, to start off, let's remind ourselves the equation for centripetal acceleration. Centripetal acceleration is the tangential velocity squared divided by the radius. So right here, like from the start, we have a couple of variables we should go over. So let's say we have an object and the object is spinning around in a circle. Okay, centripetal velocity is the velocity that the object is going at that exact moment. All right, so I could have the object going, it's kind of at like 2:30 o'clock, right? Or if I have it right there, we can have the tangential velocity like so, right? Just fully going perpendicular to the circle. So that's the big idea. It has to be perpendicular to the circle. And the next arrow that I'm going to draw, so these are my centripetal accelerations. Now notice my centripetal acceleration is just pointing straight into the circle. Now when you draw these, okay, I'm going to draw a couple more of the objects moving around a circle. Make sure that your tangential velocity is perpendicular to the circle. So in this case, perpendicular to the circle means I'm going straight down. Okay, in this case, perpendicular to the circle means I'm going like up and to the right. Right, in this case, it's like slightly down and to the right. Right. So every time you have a tangential velocity, it has to be perpendicular to the circle and perpendicular to the centripetal acceleration. And the centripetal acceleration always points towards the middle of the circle, always. All right, so here we have different scenarios of tangential velocity and centripetal acceleration. Now, if we were to cover the definition of acceleration, we know that it is either a speeding up, a slowing down, or a change in direction. And we're going to focus on this because when an object is rotating in a circle, that means it's constantly changing its direction. So with that idea of the centripetal acceleration, let's combine that with centripetal force, because we know, according to Newton's second law, that the outside net force being applied to a system will cause it to accelerate. In order to come up with a centripetal force equation, net force equation, we just add a little subscript c for centripetal. So that just tells us when we're creating these equations that we have a object rotating in a circle. So what this means is that there are forces, okay, forces, not a centripetal force, but forces that will cause this object to move in a circle. Okay. Now, notice how I chose my words carefully. There is no such thing as a centripetal force. A centripetal force is a net force. All right, so this is a net force. A net force is not a real force. Not a real force, but more rather is a combination of forces that causes a object to accelerate or a system to accelerate. So you might be asking, well, what are real forces, Mr. Lee? Real forces belong within the centripetal force equation. Real forces include stuff like force of friction, force of gravity, also known as the weight, right? We have the normal force, and we just learned about the gravitational force, right? So these are all real forces, and these real forces belong in the centripetal force equation. So to sum it up, real forces that cause a system to spin around in a circle are part of the centripetal force equation. Okay? All right. So with that equation, right, we have this equation. I'm gonna clean this up a little bit over here. we should be able to substitute our equation for centripetal acceleration that we see up here in right there. And it will look something like this. The centripetal force is equal to the system's mass times the tangential velocity squared divided by the radius. All right, so these two right there, boom, star that. That is what we are working with. All right, so that's the definition and the idea behind centripetal forces. Let's come up with a couple of examples. First example, we just have a object. Let's say we have an object, hello, and this object is rotating it around in a circle, like so. Circle, important, centripetal. All right, let's say there's a couple of forces. Let's say we have f of 1. Ooh, let's say we have this little tiny little f of 2. Hello, f of 2. Let's say we have this f of 3. Hello, f of 3. And we have f of 4. And we have f of 5. Okay? All right, so we have these 5 forces acting on this object, and this object is rotating. This is what we know. So in order to come up with your net centripetal force equation, there's a couple of things. One, identify the center of the circle. Okay, not this circular object, but the path. So I will do that in red. Boom, right there, center of the circle. Now, any force that is pointing either to the center of the circle or away from the center of the circle is considered to be a centripetal force. Now what I mean by that, I'll highlight it. If this is the center of the circle, right there, anything along this highlighted portion is considered to be centripetal. Okay, any of these forces that is along this highlighted axis is considered to be centripetal. Now just in case you're wondering, well, what is the axis? I will draw that in dotted. Anything along that axis is considered to be centripetal. All right? Now, anything pointing towards the middle is positive. But what about if it's pointing to the left? Yes, even if it's pointing to the left. Well, what about if it's pointing down? Yes, even if it's pointing down. What about if it's pointing to the right? Yes, if it's pointing towards the middle of the circle is considered to be positive. Okay, if it's pointing away from the middle is considered to be negative. What about if it's pointing to the right? Yes, if it's pointing away from the middle, then it's considered to be negative. Okay, we only care about the middle of the circle. So if I were to look at this free body diagram right here, and we were to come up with the net force equation, I'm going to start off with Newton's second law. Always start off with this. Okay, very important. Always start off there. You're going to go around the object, and you're going to ask yourself, is this a part of the axis that points towards the middle of the circle? Let's start with f of 1. Is f of 1 along this axis? Does it point towards the middle of the circle? Is it there? The answer is yes. Because it points towards the middle of the circle, it'll be positive. What about f of 2? Is f of 2 along this highlighted axis? Yes. All right, good. So we're going to put it in. Is it going to be positive or negative? Positive. Very good. Because it's pointing towards a circle. What about f of 3? Is that pointing, or is that along the axis that we highlighted? Yes. Very good. Is it pointing towards or away from the circle? Away. Therefore, it will be negative. What about f of 4? Is f of 4 along that axis? No. Very good. We're going to put it in. What about f of 5? Is f of 5 along the same axis? No. So we're not going to put it in. All right? That's what you got to do. You got to go over each and every single one of these forces and just ask yourself, if you want to do a funny voice, go for it. But ask yourself, is it along that axis that is pointing towards the circle? And if it's so, then you put it in. If it's pointing away, just make it negative. And that becomes our equation. And if you have numbers, you could plug it in. If you're like, well, Mr. Lee, I kind of like using up more ink / graphite, so I'm gonna use this formification, whatever, you know, like this is good. Well, you definitely have to start off from here. All right, so that is how you come up with the centripetal force equation. Let me try one more. Yes. All right. So we saw it when the axis of rotation was horizontal. Now let's do it when the axis of rotation is vertical. All right. So we have the object right there at good old 12 o'clock. Here's the middle of the circle. We're just going to come up with some forces. All right. We're just going to come up with, so that's f of 1. we have f of 2, we have f of 3, and you know what? Let's add a good old f of 4. All right. Okay, so we have these 4 forces. First thing you got to do, you have to identify the axis of rotation. So if that's where the object is, anything along this highlighted axis, okay, and I will even dot it in, anything along this highlighted axis, any force along that axis is considered to be a centripetal force. So if I were to come up my equation, centripetal force is equal to the system's mass times the centripetal acceleration, not squared. Why did I come up with that squared? No one knows. There we go. All right. So bring out your funny voices, right? Is f of 1 along the axis of rotation? No. Is f of 2 along the axis of rotation? Yes. So we're going to put it in. But Mr. Lee, why is that positive? Shouldn't it be negative? Because it's not pointing towards the circle. Very good. Negative f of 2. What about f of 3? Does that belong in the axis of rotation? Yes. Positive, because it's pointing towards the middle. What about f of 4? No! So we have something like this. And once again, we could break this down even more to look something like so. Let's do another one! So we did a axis of rotation that is horizontal. We did a axis of rotation that is vertical. But what if, dun dun dun, we have an object that is rotating around in a circle. Right? We have a middle right there. Let's say it's like right there. Right there. All right. Let's come up with some forces. Some forces. Let's say this is F1. Let's say this is F of 2. And let's say, I don't know, this is F3. And let's say this is F4. And let's say this is F5. And let's say this is F6. Okay. So, once again, you're going to start off from the object and you're going to identify the axis. This is my axis. This is my axis of rotation. And once again, I will do this with dotted lines. Dot 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 dot. Anything, any force along that axis of rotation belongs in my centripetal force equation. Bring out your funny voices. Centripetal force is equal to the mass times the centripetal acceleration. Does f of 1 belong? No. What about f of 2? No. What about f of 3? No. What about f of 4? No. All right. What about f of 5? Yes, yes. F of 5 belongs. Now, is it positive or is it negative? Positive. Very good, because it's pointing towards the circle. What about f of 6? Yes. Positive or negative? Negative. Good, because it's pointing away from the center of the circle. So that right there becomes our net force equation. Wow. Now, students of mine, I'm going to give you a little sneaky challenge right here. Let's say we have a force. Whoa. And we're going to call this force F of 7. Right? And F of 7 makes an angle theta. Angle theta with the axis of rotation. Okay, so in this case right here, f of 7, it doesn't belong in this axis, but there is a, I'll do this in red, there is a vertical component. Okay, I'm going to do this dotted right there. Okay, dotted. This is f of 7, and so this is cosine of theta. And so the cosine of theta will belong. Will you have anything like that? Not necessarily, but just in case you do, it's right there. Okay, and we do the cosine of it because if that is theta, this vertical component is adjacent to that. All right, so that becomes our equation. Isn't that pretty easy, right? All right, now how does this apply to us? Well, believe it or not, in our world, more things move in a circle than in a straight line, right? If you swing your arms around in a circle when you're walking, your legs are moving in a, like, this is a pendulum, right? It's moving in a circle, right? Right now, we're Earth. Earth. That's a good place to start. Let's go to our Earth. Hello, Earth. Boom. Look at that. Yes, big Earth. Big Earth. Earth. Right, and our Earth has some oceans, right? And our Earth has here. There's Europe, there's Asia, there's Africa, there's North America, South America, Antarctica, North Antarctica. All right, so we have, that's our Earth. And orbiting the Earth, we have our wonderful rock in the sky, our very own satellite. Hello, and we're going to call this little satellite the Moon. Hello, Moon, right? And the Moon is orbiting the Earth in a circular path. Oh, cool. Now, let's just imagine this was a correct circular path. Now, let's go over the check boxes. All right, do we have a circle? Yes. Do we have forces? Yes, we do. In fact, in the previous video, we learned about the gravitational force. So if I were to draw a free body diagram, the Moon is being attracted to the Earth by a force called the gravitational force, F of capital G, like so. And therefore, we should be able to come up with the centripetal force equation. All right. The only force that's acting on the Moon from the Earth is the force of the gravitational force. We had the mass of the system, which is the Moon, okay, because we're focusing on the Moon and not the Earth. And we have the centripetal acceleration. Now from there, we can expand it even more, because we know that the gravitational force is the gravitational constant, mass of the Earth, mass of the Moon, divided by r squared is equal to mass of the Moon times the tangential velocity of the Moon squared divided by the radius. Whoa, look at that. Put that on your fridge. That's something to be proud of. Now, if you're like, Mr. Lee, I want to do some math magic. Well, let's go for it. So we have the mass of the Moon on either side, so we can cancel that out. Cancel, cancel, right? We have radius in both denominators, so we can cancel one of them out. One, and therefore we are left with the following equation. Would you look at that? Ta-da! Now we can figure out the velocity of the Moon. We can see how fast the Moon is orbiting the Earth. Or if we know how fast the Moon is orbiting the Earth, we can actually find the Earth's mass. Really cool stuff, right? All right. So ladies and gentlemen, that is the end of this centripetal force equation video. We learned how to set up the centripetal force equation by looking at the axis of rotation. We learned how we can apply the centripetal acceleration, and more importantly, we also connected how the gravitational force can be used to describe our Moon, which is in a rotational orbit around the Earth. I'll see you next time. Bye-bye.